Good morning. Hi, this is Chris Aker, and this is the Data Management Best Practices webinar. My name is Chris Aker, and I'm the Data Curation Librarian at Hodges Library. I have a co-host with me today, Joy Pennica-Brucha-Roberts. Joy is the head of our cataloging department here in Hodges, and she will be talking about metadata later on. And so I'm always glad to have Joy with me, as she has lots of great knowledge about metadata. So today, just to go through a brief outline of what we're going to talk about, I'm going to start talking briefly about why it's important that you manage your research data well using some commonly accepted best practices. And then why it is important and encouraged by most research funders these days that you share your research data that they fund, and why data sharing in general is a good practice. We're going to go over some data entry and data manipulation best practices that help you ensure that your data are good quality. And then some quality control and quality assurance tips and tricks that you can employ to find errors and correct those errors. And then I'm going to talk about backup and preservation of research data, and some tips, some rules of thumb that I like to talk about there, and why that's so important. And then Joy is going to step in and talk some about metadata and why it is so important to research data. And then we'll finish up with some data citation best practices. So why is it important that we manage data well? You want to manage data for yourself to keep yourself organized. It helps you be able to find your files, your data inputs and your analytical scripts and your outputs at various stages of the analytic process. It also helps track your science processes for reproducibility, to be able to match up your outputs with exact inputs and transformations that produce them. Helps you better control your versions of research data, to identify different versions easily that can be periodically purged or reproduced if needed. It helps you control the quality of your data more efficiently. And data is a valuable asset, not only to you, but also to the university. So it's expensive and time-consuming to collect, and so you want to make sure you manage it well to maximize its effective use and the value. And you want to continually improve upon its quality, and which improves its accuracy and integrity, and will improve its relevance and usefulness and help better facilitate data sharing. And all this helps ensure sustainability and accessibility in the long term for reuse in science. I just want to pause for a moment and make sure that everyone is hearing me clearly. I've had a question in the chat about possibly that someone can't hear me. Okay, good. I just wanted to make sure. So in summary, the goals of effective data management are to get data that are well organized, both within the files themselves and the groups of files. You want to make sure they're documented adequately with metadata, preserved for future reuse, accessible by others for that reuse, and accurate and valid. And if data are all these things that I just mentioned, then you will have high quality research data that is easy to share and reuse in science. The data then can be cited by other researchers, which will add credibility to you, the researcher who prepared them. And overall, it saves time and money and advances science. In addition to making your life easier, one of the main goals of effective data management is to facilitate data sharing with other researchers. Grant funding agencies want to see a higher return on their investment, and seeing data collected during projects that they fund get shared with other researchers lets them know that data is having a broader impact. So let's talk about data sharing and why it is important. So why expend the extra effort to share data? Well, because it benefits the public, the research sponsor, the research community, and perhaps most importantly, you, the researcher. How does the public benefit from shared research? The more informed the public is, the better that they are able to understand and contribute toward effective public and personal decisions. The public needs data to help with environmental and economic planning. Data help inform federal, state, and local policies. And the public can use data to help with social choices, such as who they'll vote for, or how they want to use their tax dollars, and when and where they will send their children to school. It can even help them make personal lifestyle choices and health choices such as exercise, smoking, and nutrition. So why do research sponsors encourage more data sharing? Because sponsors have an obligation to maximize the investment of research dollars. Data sharing enhances the value of research investment by enabling external reviewers to verify the project performance metrics and outcomes. This not only increases the credibility of the data, but also spurs new research that can build upon the initial investment and advance the science rather than duplicate expenditures. The scientific community as a whole also benefits from sharing among researchers. Data sharing allows researchers to build upon one another's work and to further rather than duplicate science by exploring new findings or combining findings into meta-analyses that cannot be performed or done with individual data sets. And in sharing research data, the scientific community expands both individual perspectives and the collective comprehension. Access to related research enables members of the scientific community to better reproduce, compare, and assess methods and results. Scientists are able to learn from one another and educate new researchers as to the most current and significant findings within their fields. Finally, the value to you as a researcher. How does the independent researcher benefit from data sharing? When scientists share their data, they gain recognition as an authoritative source and respect as a wise investment for research dollars. When data are exposed, feedback from the broader community can then be used to improve the quality and presentation of the data. Shared data also allows for greater opportunity for data exchange and networking opportunities with peers and potential collaborators. Now, one of the most important things one can do when managing their research data is to take steps to ensure that data entry, processing, and analysis are done in such a way as to minimize error. We'll talk now about ways to do that during data entry and manipulation. But before I move forward, let me check the chat. I do have a couple of things here, some questions. I will answer the question about UTHSC in Memphis later. And I'm sorry, sir, about the sound issue. I'm not sure what's going on with that, but I need to go ahead and move on. The goals of data entry are to create data that are valid or have gone through a process to assure quality and or organized to support the use of the data and for ease of archiving. Many researchers like to manage their data in Excel. Excel makes it easy to use poor data management entry processes. Excel doesn't enforce any rules upon you or your data unless you tell it to do so. These data, shown in the spreadsheet, are entered into Excel from a small mammal trapping study. Each block of data represents a different trapping period. Inconsistencies in how the data were entered from each sampling period make the data difficult to analyze and difficult for anyone but the data collector to understand. Well, note that the date is listed in different places within each block. Date is a column in the first block, but listed as a header in the block to the right. Inconsistent date formats are also used. In one place, the date is formatted as day-month-year, with the first 3 letters of the month spelled out, while elsewhere, the format is 2-digit month, a 2-digit day, and then a 4-digit year. Also note that the order of the columns is inconsistent. You have site, date in the first block, and then you have site and plot next to it in the block below that. And then even the column headers are named different things. You've got species called species in the first block and rodent SP in the block in the top right. Further, you have the weight labeled as weight in one block in the top right, or actually in the 2 blocks on the top, and then on the block on the bottom you have it listed as grams, so the units of the weight instead of the name of the weight. So this can be confusing to any user who has to try to make sense of these data, and it would be a nightmare to try to write metadata for this spreadsheet. There are still more problems with how these data were entered. The naming of the sites is inconsistent. For instance, deep well was used in the first block versus DW in the block to the right. The file contains several typos also, such as Rio Salado versus Rio Salado. A human can figure this out while looking at these spreadsheets, but the names would have to be harmonized for a statistical program to be able to use it. It would be easier to filter for just deep well with a space and not have to know that you also need to filter for deep well with no space. Similarly, in one place, a species code is capitalized PERO, whereas in other parts of the spreadsheet it is in lowercase PERO. Further, in the first block, you have a mean that was calculated for the weight of the rodents. The value for that mean, called mean 1, is in the same column as the weights of the individual animals. In later manipulations of these data, it would be easy to copy that value as though it represented the weight of a single mammal. It's bad practice to mix types of information in one column. It is best for raw data to be maintained in one file and then the calculations on that raw data to be done in a separate file. In addition, you have text data mixed with numeric data in the single column called weight. It says escaped less than 15 presumably indicating that a rodent less than 15 grams escaped. A statistical program will not know exactly how to deal with text data mixed in with numeric data. What is the mean of 12, 91, and escaped less than 15? It can't be calculated. To analyze all these data using statistical software and to make it much easier to understand by any user, these data need to be organized into a column for each variable. Therefore, it's essential that only one type of info be entered into each column, and that spellings, codes, formats, etc. are consistent. This shows the same data entered in a way that would make it easy to understand and analyze. The data are not entered into separate blocks, but arrayed into a single worksheet. They are entered in one table with columns defined by the variables date, site, plot, species, weight, adult, and then comments that are recorded for each sampling event. The columns of the data have consistent types, and each column contains only numbers, dates, or text. You've got consistent names, codes, and formats used in each column. For instance, all the dates are in the same format, 2-digit month / 2-digit day / 4-digit year, and there are no typos in the site names. Species are also all referred to by standard codes. Therefore, if the user wanted to subset the data for the species that equals PERO, they could easily filter the file for just those data. Additionally, there are only numeric data in the weight column, so a statistical program or Excel could readily calculate statistics on that one column. And preparing metadata for this file would be fairly straightforward. Now that data is in much better shape in that spreadsheet to the right. However, if I were helping this researcher prepare this file for archiving and preservation, there are two additional things I would ask them to do differently. First thing would be, I would ask them to add the units to the weight column. As it stands, we can't really tell what the units are. And the best practice for doing that would be just to put it within the column header. So I would put weight and then parentheses grams. And the second thing I would ask them to do is to put the dates in that first column A in the ISO standard date time format, which I will talk about in the next slide. A best practice in data entry is to create descriptive column names without spaces or without special characters. Sometimes statistical programs have special uses for some special characters, so you want to make sure that to avoid them whenever possible in your data file. So for instance, a file named field visit 1 _ small mammal data _ 2010-04-11 indicates that this file contains data collected during field visit number 1. And it contains small mammal data, and the version is dated April 11th, 2010. And we know that it is April 11th, 2010, rather than November 4th, 2010, because it uses the standard ISO date time format that I alluded to in the previous slide, which is the 4-digit year - a 2-digit month - 2-digit day. And so this file name is much more helpful and much more descriptive than simply mammaldata.csv. Now, there's a lot of great things about spreadsheets, but one must be wary of problems that can arise from their use. Spreadsheets, for instance, can sort one column independently of all others. The data entry person for the upper spreadsheet elected to leave empty cells for site, treat, web, plot, and quad, it's obvious to a person, to a human, why, and it doesn't necessarily cause that person any problems if simply just looking at the file as it is. However, if someone decides to sort on species, it's no longer clear which species maps to which time period or to which measurements, and this could make the spreadsheet unusable. It's good practice to fill in all the cells when using a spreadsheet for data entry. So a best practice when inputting data within a spreadsheet is to enter complete lines of data so that the data are sorted on one column without loss of information. When you collect data, you are bound to have some data points with no values. There are ways to ensure that those values are consistent and don't throw off your analysis. A preferred way to identify missing data is simply to leave the field empty. If for some reason an empty cell is not possible, for example, the software that you're using requires something to be there, then use an impossible value such as 9999 in a numeric field, and in a text field, use NA for not applicable or not available. If you need to explain something else and something in addition to the data, you can use a data flag in a separate column to qualify an empty cell. For instance, in this example of stream chemistry data, you have a flag M1, which indicates that the sample was not collected at that time interval. You also got a flag E1, which indicates the value that you see there is estimated. So in the metadata file or the README file that you create for to accompany your research data, the information about those flags would be contained within that file, so you would be able to define what they mean. As I said, Excel is a very popular data entry tool, and it does allow you to enforce some data validation rules. For example, here you've got a drop-down menu list which has been generated that allows the user to only select entries from a predetermined list of variables. In this way, only defined species codes get entered instead of having to type those codes in each time. So therefore, the data are consistent. And you create the predefined list by using the data validation tool, and you select the validation criteria list. You'll have a list of predetermined species, for example, and another part of the spreadsheet that you select as the source input list for that pull-down menu. Here's another example of using data validation tools within Excel. The height variable has been defined to contain only values between 11 and 15. So for when 20 is entered, the user is told that they have entered an illegal value. So using this type of tool is helpful if you know ahead of time that a value within a column will not fall outside that range of 11 to 15. Of course, if that kind of information is not known ahead of time, the validation tool would not be helpful. But if that is known, you might as well put the guardrails on it so that people can know when they put in a legal value. Some researchers use database software instead of spreadsheets for their data management needs. Databases are a powerful option for storing and manipulating data sets. These are some of the pros and cons of spreadsheets versus databases. Database softwares include programs such as Oracle, MySQL, or SQL Server, or even Microsoft Access. Spreadsheets are good at making charts and graphs and doing fairly complex calculations. They are easy to use, but they can become unwieldy as the number of records grows and a dataset becomes very complex. Databases, on the other hand, work very well with high volumes of data, and they are much easier to query in order to select data having particular characteristics. They also maintain data integrity. That is, one column cannot be sorted separately of all the others, which can happen within spreadsheets. Databases also enforce data typing, which is a best practice. This means that only data of a certain type, for example, text, can be entered into a column of type text. This helps prevent data entry errors. Now, one drawback to databases is that they do have a steeper learning curve than a spreadsheet, but there are many benefits to it. A relational database matches data stored in tables by using common characteristics found within the dataset. This helps preserve data integrity and also makes it possible to flexibly mix and match data to get different combinations of information. A dataset consists of a list of tables, and each table has a defined relationship with another table or tables using a common piece of information called the primary key. Databases also have a powerful command language for querying and manipulating information called Structured Query Language, or SQL. Here you see a data set for plant phenology has been divided into 3 tables, one describing the site information, one describing characteristics of each sample, and one describing the plant species found. Relational databases are currently the predominant choice in storing data like financial records, medical records, personal information, and manufacturing and logistics data. Database features includes explicit control over data types and have the advantages of quality control and performance. Here in the plant phenology table, only dates are allowed in the date column, only text is allowed in the site column, only real numbers are allowed in the height column, and if a user tries to enter a question mark, for example, under the flowering column, the database will reject the entry because it will only accept a Y or an N. So this is useful for defining how data is to be entered. Relationships can be defined between 2 sets of data, or in this example, between 2 tables. Suppose that you have 2 tables used in the plant phenology study, one for observations and one for sites. And you want a 3rd table that contains both observations and the latitude and longitude of your sites. Because both tables contain the site info, they can be joined together to create a 3rd table containing the info that you want. Database features also include a powerful command language called Structured Query Language. These are just a couple of examples of what you can do with SQL. The table at the top of this slide is called soil temp in the database. You can write an SQL command that returns all the records collected on February 1st, 2010. And so this SQL line is how you would select the data from the top table to create the secondary table with just the records collected on that specific date. You also can create a select statement that returns all records from the table soil temp, where the treatment equals N and the sensor depth equals 0. So from this example, you can get a sense of how easy SQL is to use to subset data based on different criteria. You can even run calculations on the data within the tables and use the calculated values to create new tables. Forms are a simple way to aid in data entry. Forms can be created that make entering data into a relational database as easy as entering it into Excel. The screenshot you see here shows embedded forms that were quickly generated in Microsoft Access for adding data to the 3 tables in a database of plant cover measurements. So, in summary, be aware of best practices when designing data file structures for your data sets. Choose a data entry method that allows validation of data entered, and be sure to invest time in learning how to use a database, especially if your data set is large or complex. If you're interested in learning how to use a database software, OIT, our Office of Information Technology, provides training on the use of some database software programs. Okay, so now you've taken steps during your data entry process to minimize the possibility of data error. But that doesn't mean you need to stop there. There are other ways to help with quality control as well. In general, there are 2 types of errors that can occur within a data set. First, you have errors of commission that are the result of incorrect or inaccurate data being included in the data set. This may happen because of a malfunctioning instrument that produces faulty results, or data can be mistyped during entry, or there are other problems that can happen to cause errors of commission as well. Errors of omission, on the other hand, are the second type of error. These result from data or metadata being omitted. Situations that result in omission errors are when the data are inadequately documented, when there is human errors during data collection or entry, or when there are abnormalities in the field that affect the data. The remainder of this module will cover best practices for quality control and quality assurance for the different stages of a research project. First, before data collection, a researcher should think about defining and enforcing standards that will be used during the project. Consider formats that will be used for the data tables or the data entry forms. Also, if abbreviations or codes are used, they should be defined up front. Measurement units should also be specified, and relevant metadata should be identified before data collection. Second, you should assign responsibility for data quality before collection begins. Ideally, the person responsible for data quality assurance and quality control is the same person collecting the data and is educated in the quality control and quality assurance methods. Consider using techniques that help eliminate mistakes during data entry. Examples are using double data entry, where non-digital data are keyed in by 2 people independently. Differences in entries can then be detected via computer programs and examined further for mistakes. Another way to reduce data entry error is to record yourself reading off the data and then transcribe it from the recording. You may also use a text-to-speech program that reads the data to you while you type it into a computer. If you are using spreadsheets or databases, you should carefully consider their design before and during data entry. Use consistent terminology within the database and atomize your data. This means only one piece of information is entered into each cell of the spreadsheet or database. Multiple pieces of information embedded in a single data cell will be problematic later during data analysis. If you are using a database, restrict what can be entered into the database. For example, set up a field that will only accept text or only numerical values, or choose a maximum number of characters or a range of values that a field will accept. Finally, document any changes made to the data. It saves time if good records of data editing are kept, since multiple users are less likely to spend time on error checking with older versions of the data. If mistakes in data editing or cleaning are made, good data records will allow these mistakes to be undone more easily. Documenting data changes may be as simple as creating a text file to accompany a dataset, or it may include using a scripted programming language for correcting errors so that each step taken is clearly documented. Once data are entered, basic quality assurance measures can be taken. First, if data are in spreadsheets or databases, be sure they line up in their proper columns. Also, check for any missing, impossible, or anomalous values. One way to check for these problems is to sort data fields and check for discrepancies. It is often also useful to perform basic statistical summaries, such as means or standard errors. If data transformation was performed during an analysis, compare the statistical summaries before and after transformation to ensure that no mistakes were made during the transformation. Another strategy for quality control after data are entered is to look for outliers. Outliers are extreme values for a variable. Extreme values are those that lie outside of the statistical model being used to describe the data. Keep in mind that the goal is not to eliminate outliers, but to identify potential data contamination. An easy way to do this is to plot your data on a graph. In this graph, most of the data fall along the black line. The outlier identified with the red arrow should be flagged for further investigation. You may find that the data point is legitimately correct, in which case you would keep it. But you may find that it's the result of a typo, and in that case, you would have the opportunity to correct it before it messes up your analysis. Another common strategy for identifying outliers is to use graphical methods, for instance, normal probability plots, regression, or scatter plots. And if the data are geographical in nature, mapping the points can be used to ensure latitude and longitude were correctly entered. This map shows an example of an error that is the result of misentering latitude data. Another method for identifying outliers is to use statistics. You can look at the deviation of a value, which is the difference between the observed value and the mean of that variable. By subtracting values from the mean of a data set, the presence of outliers or faulty data points can become more apparent. So we first define several concepts that are important for understanding quality assurance and quality control. And this includes data contamination and the types of data errors that can result in poor quality data. And then we covered some best practices for quality assurance and quality control. These strategies prevent errors from entering a data set or identifying those errors if they are present within the data. It's very important to define and enforce quality assurance and quality control standards before, during, and after the data collection and data entry. Now you've made sure that your data were entered properly and you've cleaned up the data from errors of commission and errors of omission. And now all that hard work could be for naught if you don't have a good backup plan. The main difference between data backups and archiving is that backups deal with data that is copied elsewhere and potentially can be overwritten again as the data change. Archiving makes a record of data that is usually in its final state. When a user performs a backup, they are in essence taking a snapshot of the data at that moment in time. This allows the user to restore the file as needed, such as when the current version of a file becomes corrupted or lost, somehow destroyed or altered. Backups are often used for short-term storage and near long-term storage, depending on the user's backup needs and procedures. Backups are usually scheduled on a frequent basis. Archiving, on the other hand, deals more with records that are no longer in use and is used to create a historical snapshot of the data. This provides for preservation of the data for future needs. Usually, archives are made when a project ends or at other appropriate times, such as at a project milestone. Regardless of whether you're dealing with backups or archives, you should have multiple copies in case one or many versions fail. There are many reasons to perform backups, which includes mitigation or to prohibit the loss of data, which may or may not be reproducible. Save time, money, and productivity, as little to none of the data will have to be reproduced. Having a backup already in place means you are prepared for when the unexpected happens, such as human error, disasters, or computer failures. It allows you to go back to earlier versions and to see what your results were. For example, if you are creating models and you use data from an earlier model to run, the most recent file you have on your computer may not have the same data as when you first created the model output. It provides for the ability to send older files to others, regardless of the current version or state. For example, if the current version has been corrupted. And it may allow you to respond during times when questioned results were based on older versions of the files. For example, you may find that you will have to justify your results in court or to other scientists. By having access to older files, you may be able to respond to their request for information better. Or you may not be able to reproduce the data, and the original copy may be the only evidence of the data collection. Our last topic covers data preservation. Data preservation is a comprehensive topic which includes things such as backups, archives, data conversions, reformatting, and rescue. Data rescue deals directly with older files that may no longer be in a format that is easily accessible and will require some rescuing before it can be used again. Data rescue becomes more and more important as projects end. Even if data was being preserved through the lifetime of a project, often files go untouched or orphaned. Frequently, data has not been managed properly and requires some form of data rescue to be performed so that the data isn't a total loss. So, when preserving your data, you need to consider many things. Consider data formats. It is best to use non-proprietary and standardized data formats. This will better ensure readability into the future. Be sure to check files after converting them, as sometimes data, metadata, and formatting loss can occur. You need to be aware of versioning. Make sure to use some sort of naming convention, such as incremental letters or numbers, to keep track of file edits and revisions. This will also help you more quickly locate the correct version of a specific file. And be aware of file naming. Use file names that are consistent, descriptive, and concise. Many software programs use a generic file name as their default file output, and usually these names are not are too general to be useful. Then here's some examples of file names that, for example, the one on the top in the red is, I would consider, not a very good file name because it uses some random date format. The file name in orange is better. I would consider that a good file name. It does use the standard date time format. You can even get very specific on that ISO standard date time format if you need to, with adding the time and the time zone into the ISO format. That may be overkill for you, but just know that it is possible as part of the ISO standard. Another best practice is to create a backup plan. This may be a physical document or a web page, and preferably it is listed as someone's specific job requirement. Regardless of how you create it, it's important to address any of the previously mentioned issues and concerns. For example, who do I contact when I need to get a file off of a backup? I will include a data backup and security checklist in the chat momentarily for you to use to create a policy or a backup plan. Once you have a backup plan in place, it is good practice to review it periodically to ensure that information still has value and is applicable. Hardware, software, projects, and staff can all change over time, so it's always good to have a written plan in place ahead of time. We're going to move on now to the metadata section, and I will turn it over to Joy. And then when Joy is finished with her section, we'll come back and talk about data citation. Okay, Joy, you are unmuted, and I'm going to mute myself, and then you can take over from here.
Well, thank you, Chris. Good morning. I hope you are all doing well so far. My name is Anjali Panikabut Roberts. I go by my Thai nickname Joy, and I am the head of cataloging at the University of Tennessee Libraries. You can contact me via the email. That would be the best way to get in touch with me at apanigab@utk.edu. Chris, I still can't get the remote.
Click on the screen before you try to advance the slide.
Okay, I got it. Thank you. So today I will be talking about metadata for data set and data management. So what is metadata? Metadata is a structured information that describes, explains, locates, or otherwise make it easier to retrieve, use, and manage an information resource, including the data set. Metadata is also data in any format. It describes the content, quality, condition, and other characteristics of a data set. It's also a data reporting. So metadata records answer questions such as, why was the data set created? What process we used to create the data set? What projection in the data in? What was the data last updated? Who created the data? What scale was used? Fields that are in the table of the data sheet that Chris had gone over with you. And what do the values in these fields mean? And who do I contact about getting more information about the data? And how do I obtain a copy of the data? The access type, are they restricted or open or embargo in any way? And do the data cost anything? And are there any limitation to the data, such as, like I mentioned earlier, the embargo or not? So metadata is a valuable tool. The metadata records preserve the usefulness of data over time by detailing methods for data collection and dataset creation. Metadata greatly minimize duplication effort in the collection of expensive digital data and foster the sharing of digital data resources. This is very increasingly more important in the age of big data and also for funding agencies' requirements for data management plan in research proposal. You can see metadata in real life around you. So if you're listening to podcasts, you may see the metadata in your MP3 files. When most food items now have nutrition facts and tell you the information about calories, vitamin, and so forth. Or when you search a library catalog, you can also see metadata for books and media and other information we provide in the libraries. So, but what do we do when we create a metadata? Why do we have to have something like metadata standard? With a big community of data users, we need to establish metadata standards for interoperability. And metadata standard is an established standard that provide common terms, definition, and structure that allow for consistent communication, not only for data exchange, but also for human readable information as well. The use of standards also supports search and retrieval by computers and database systems, oftentimes across multiple systems and data repository. For example, for control vocabularies for dataset, I will discuss some example in the future slides of Pangaea database, for example. Metadata is also a major part of data policy, as I have discussed about research agency requirements earlier. For example, from the project Open Data that requires the use of Common Core metadata, it specifies that metadata should also include information about origin, link data, geographic location, time series, continuation, data quality, and other relevant indices that reveal relationships between data sets and allow the public to determine the fitness of the data source. This guideline requires certain attributes of the data to be recorded to provide access to the data set, as well as to allow potential users of the data set to evaluate if the data set would fit their data information needs. Here is an example of the metadata standard or schema for data sets from the DataCite, which is a universal metadata for data sets supporting projects such as Open Science used for OpenAIRE, a European project supporting Open Science, and also Zenodo from the CERN, the physics, the lab that, and these are for their database of data set and also other research information. The metadata requirements are quite basic here, you can see, but they're not disciplinary specific, but you can see that these are metadata designed for research data sets, such as the version or funding references. And I also include one link here about the NSF Dear Colleague letter. It's it was published in just during May this year, and it does require, so it starts to require more and more metadata, especially for this Dear Colleague letter. It requires you to, NSF say it encourages you, but at the end it say, well, you need to also provide persistent identifier for your data set when you submit the research proposal. So there are a lot more requirements with the metadata from the research agency as well. So what does a metadata record look like? This is an example of a metadata that uses the Federal Geographic Data Committee or FGDC standard. The benefit is that if every geographic data set use this standard metadata schema, then the dataset's information can be shareable and searchable by the computers. The metadata is also data documentation, as you can see that the description includes the research methodology and the data description. The purpose describes the rationale for the research. Here is another example for the disciplinary specific data sets for paleontology at the American Museum of Natural History. The metadata used in this database reflects the specific aspects of the discipline, from the identification by the biological classification, in this case it's Crocodile, and then an order of large reptiles, and the components of the fossil, location, collector, time period, and the rock units the fossil was found. The Pangea database is another example to show the metadata structure and elements that used by the Earth and Environmental Science. They require a different data set that match for this discipline. And you can use these metadata elements to describe something like the ocean drillings data sets with the expedition location by latitude and longitude, for example. So this is one of example of the Pangea data set. The metadata are used to describe the data and also as search facets, filter, as well as for mapping and visualization of the data. In this example, you can see that from the deep sea drilling project, the process smear slide data is derived directly from the smear slide data collected on board of the Glomar Challenger, which is a ship. And each smear slide represents a small portion of sediment distributed on a glass slide for the microscopic evaluation of the mineral and fossil composition. In the database here, you can see the ship's name, expedition's name, the events with latitude, longitude, location in the ocean, the size of the drill's core, and the parameter or the physical properties of the rock and sediment collected from the drill that they collect on the smear glass analysis. These metadata and the elements are used in the search interface design and visualization as well. The image you see here for the map of the drilling site in the Red Sea is from the georeferences, the latitude, longitude, and location metadata to get the Google map. And for the interface, when you get to play around with this database, you can choose the mineral volcanic glass, and if you click on that, you can pull up the search result for the other data sets that have this parameter. And also you can see the facets from the result created from metadata. So metadata can be used for both human and the machine retrievability. Nowadays, with your research ID such as ORCID or ORCID, you can also add your data citation to your ORCID account to link back to your data sets, like in this example in the Pangea database for Alice Lefebvre, one of the researchers contributing to this data set. Creating your ORCID IDs to add your datasets metadata and publications also facilitate linking and sharing of your datasets information with the funding database. At UTK, we have PIVOT, PIVOT, and other international name authority database that we use in our libraries internationally, from the Library of Congress Name Authority file and virtual Name Authority file. And also for your own portfolios for evaluation. I added a LibGuide of ORCID at UTK to this slide. When you come back to retrieve the recording later, it's at libguides.utk.edu/ORCID. So ORCID is also interoperable with the pivot and element. It will automatically update your pivot and element accounts when you add new information. And as we are in more and more visual society in data as well, we see more and more visualization tools. So you can see that in this example on the list I show you here, you can see some, you can see that there's a SciMaps at the Smithsonian Institute, which has built upon mapping scientific progress via a data visualization. Bonner's book, Atlas of Knowledge, is based on this project at the Smithsonian. Carto is another mapping application you can use to visualize your data and plot them on the online maps. It is popular among geospatial digital humanities, which is a specialization of my colleague, Dr. David Joseph Risley. He's Associate Professor of English at the American University in Beirut. I like to show this interesting and fun project by DJ. He studied linguistic landscape of Beirut, and he studied the document and analyzed how multilingualism is expressed in a written manner in public space. The LLB project brings together more than 2,000 written language samples in Arabic, English, and French from the Greater Beirut area. Each data point on the map has a metadata for the language and the scripts and the geolocation of the images taken from a mobile phone with the app called Fulcrum that works with the Carto mapping app. Another example from Cornell Lab of Ornithology, the metadata for species, date, time, and place of bird observation are used to generate this map from the bird observations data. This map is based on the selected metadata for Knoxville, Tennessee here for the birding hotspot for the blue herons year-round during 2018 to 2019. Here's another example how the metadata or the data description is used to provide keywords for these data visualizations research tool for patents from the U.S. Department of Energy. I add here some additional resources for you for different disciplinary metadata. You can explore this website. And also for the U.S. government Open Data Project, these are additional resources for disciplinary specific metadata, especially for the data sets submitted to the U.S. government agencies. So for me, in conclusion, I think it's best for you to plan for metadata early on at the beginning of your research process, along with your data collection process. It will ensure that you will have the accurate data information for your data sets and also for data citation for your data users as well. And on that note, Chris will continue to talk about data citation. And if you have any question or anything I can do for you, please also contact me anytime. And thank you so much for your participation in this workshop. Thank you.
Thank you, Joy. Let's see. All right, so the last section I'm going to briefly discuss today is data citation. Similar to how you would cite a published article or a book resource in any of your research, you would also do the same for a research data set that you reused that were created by a different researcher. You want to provide the information within a citation that's necessary for someone else to identify and locate that data set. Currently, there are no standards. However, we are getting closer to standards. There are some international organizations, one of which is called the Research Data Alliance, that is working towards some data citation standards. However, those are not published yet, but if you are publishing within a specific journal, or if you're a member of a specific disciplinary professional organization, you may find some data citation recommendations within for a specific journal or a data repository or your professional organization. Now, data citation looks basically identical to a citation of any other type of resource. You have the data creators. That's what we call those who collected the data and created the data set. That is the equivalent of the author in a regular citation. The date, that's the date the data were collected or published, and sometimes it can be one or the other, but that specific date is usually the date that it is published. And then you have the title of the data set. Sometimes if you reuse a data set from another researcher, they may give you the name of a data set. It may be a data set that accompanies a journal that you have located, a journal publication that you've located. And so in that case, you would name the data set data from, and then the name of the article from which that data were connected. And so in this case, the data set, or the data set is connected to an article within the PLOS One journal, but then you see that we have a DOI, which is that last link there, and that's a digital object identifier, which actually identifies exactly where to locate that data set. And that data set resides within a data repository called Dryad. So many journals use Dryad as the data repository. So if you publish an article in one of these journals, such as PLOS One, then you also have to publish the research data that accompany that journal article within Dryad. If a journal that you are publishing in does not have an agreement with Dryad already, you are welcome to use our internal data repository here at University of Tennessee called Trace. So that concludes the Data Management Best Practices webinar today. I want to give you just a little shout out to our group of librarians here in Hodges called the Scholars Collaborative. We can help you with any specialized data management or publishing needs that you have. A scholarly communication librarian is Rachel Caldwell, so if you have any questions about publishing in open access journals or questions regarding copyright, things like that, then Rachel would be the person you would want to talk to. Anything related to data management or data archiving and preservation, that would be me. If your project has a mapping or geospatial component and you want to use the Geographic Information Systems software we have available to us, then Eric Arnold would be your point of contact. And then anything related to audio and video editing or graphics, anything that needs those type of specialized software or devices, then you would want to talk to Michelle Brannon, our media literacy librarian. So finally, we're here to help. Here is our contact information for me and for Joy. Feel free to reach out to us if you have any questions. If you want to post questions in the chat, I'll give a few more minutes for that, and then I will follow up with you individually. What I'll do is I'll try to answer the questions as I can, and then send it out to the entire group so that everybody can have the benefit of those questions and answers. So thank you for attending, and that concludes today's webinar.